सचिन पुजेरी, अभिनंदन, अभिनंदन, अभिषेक, अभिषेक, अक्षता, अक्षता, आनंद, आनंद, अंजुम, अंजुम, बसवराज गडकरी,
प्रेजेंट सर.
राइट, बसवराज ऐनापुरे,
यस सर.
ओके, भाग्यश्री मठ, भाग्यश्री मठ, भक्ति,
Present, sir.
ओके, भारती,
Present, sir.
ओके, चेतन कुमार, चेतन कुमार, दीपक,
Yes sir.
राइट, दिव्या, दिव्या, गट प्रथमेश शिवाजी, गट प्रथमेश शिवाजी, ज्योति,
Present, sir.
ओके, किरण लिगाडे, किरण, लक्ष्मीकांत कालोजी, लक्ष्मीकांत, मानतेश,
यस सर.
ओके, मोळे प्रेम,
Present sir.
राइट, नागेश,
Yes sir.
नागेश, ओके, नंदीश, नंदीश, पूजा पाटिल,
Present, sir.
राइट, प्रमोद कुमार,
Yes sir.
प्रमोद कुमार, ओके,
Yes sir.
प्रवीण मखदुम, प्रवीण मखदुम, प्रियंका, प्रियंका,
Present, sir.
ओके, संध्या, संध्या, संतोष पुजारी, संतोष पुजारी, संतोष सोनार, संतोष सोनार, शाहबाज, शाहबाज,
प्रेजेंट सर.
राइट,
प्रेजेंट सर.
ओके, शफिया,
Present, sir.
ओके, श्रीधर, सृष्टि बर्मण्णवर,
Present, sir.
राइट, सिद्धार्थ वर्णेकर,
Present sir.
राइट, सिद्धार्थ पाटिल, सिद्धार्थ पाटिल, सुप्रिया,
Present, sir.
ओके, वंदना, वंदना, वसंत दोडमनी,
Yes sir.
ओके, वेददत्त, वेददत्त, योगेश,
यस सर.
राइट, महेश दोडमनी,
Yes sir.
ओके, बाळेश, बाळेश, तैक मोहम्मद,
यस सर.
राइट, प्रवीण राठोड, प्रवीण राठोड, ऐश्वर्या,
Present, sir.
ओके, अमानुल्ला, अमानुल्ला, बंडोळकर तनय मोहनदास, भावराव, भावराव, शोधन,
Present sir.
राइट, देवानर अनिल कुमार शेकप्पा, देवानर अनिल कुमार शेकप्पा, नंद कुमार, नंद कुमार, प्रमोद केस्ती, प्रमोद, रोहिणी पावळे,
Present, sir.
Right. Rohit Alwani.
Present, sir.
Okay. Shashidhar. Shashidhar. Sridhar Badiger.
Present, sir.
Okay. Saish. Snehal. Snehal. Vaishnavi.
Present, sir.
Okay. Karthik Yam. Karthik Yam.
Present, sir.
Okay. Anybody else join?
Roll number 22.
22. Name?
Nandish.
Nandish. Okay. Anybody else?
Roll number 3, Abhishek Karwat.
Abhishek. Okay. Anybody else? Anybody else? Okay. Shubham Meligiri. Who is Shubham Meligiri? Shubham Meligiri. Yes. Who is Shubham Meligiri? Yes, please. Who is Shubham? Just now he joined. Shubham. Yarri Shubham andre yarri? Shubham.
Sir. Smita.
Yes. Smita re.
Yes, sir.
Smita Meligiri. Smita Meligiri re. Okay.
Yes,
Okay. Right. ಆಯ್ತು. We are discussing about few of the instructions in the last class. We discussed ACALL and LCALL instructions. Are you able to see the screen here?
Yes, sir.
Okay.
Yes, sir.
Right. Return interrupt, RETI. This instruction returns from the subroutine. Okay. So whenever there is an interrupt to the microcontroller, that interrupt is requesting for servicing some job, for providing the service to that interrupt. So it will provide a request, it will send a request to the microcontroller. Microcontroller will stop whatever it is doing and it will provide the service first to this interrupt. Right. So if it has to provide the service to this interrupt, what it will do is it will execute a small program, a small subroutine called as interrupt service routine, ISR. In short, it is called as ISR, interrupt service routine. After executing this interrupt service routine, the last instruction of this subroutine or ISR is a RETI instruction. This, when it executes this RETI instruction, it will return back to the main program where it was interrupted. Let us say it is executing the main program. So the same concept I explained in the previous class. Let us consider this example of ACALL instruction. Same example we can also consider for RETI instruction. Here, instead of ACALL, let us say this is a call instruction or it is a jump instruction. Let us consider it as call instruction. So call instruction, when it is executing, right? Here, if there is an interrupt, suppose say there is an interrupt which is interrupting the microcontroller. When there is an interrupt request, when the interrupt is requesting the microcontroller to provide service to that particular interrupt or that particular work or that particular task or job. So it is requesting the microcontroller will stop whatever it is doing. Suppose say when the interrupt has arrived, let us say the microcontroller is executing at 2000 H memory location, ACALL next instruction. It is executing this instruction, ACALL next. Right. So what the microcontroller will do is it will save the memory location of the next instruction. What is the memory location of the next instruction? Move a comma hash 24H. This is stored in 2002H. It is stored in 2002H. right? So this memory location is stored in stack memory. We understood in the previous class how the memory location is stored in the stack memory. First, the lower byte will be stored, that is 02 in the first memory location, say 08H of the stack memory. It will increment the stack. In 09H, it will store the higher byte, that is 20. It will store 20, right? In this way, it will store the memory location, return memory location into the stack memory. After it stores the return memory location into the stack memory, it will load the target address or the subroutine address in the program counter, and it will jump to the target address. It will jump to target address. Here we have taken target address as 0006. 0006 target address. It will execute this small program or the small subroutine, this one. Add addc a comma rn, add with carry a comma rn, subtract with borrow a comma hash 05h. There are few instructions here. The last instruction, instead of reti, it will be re. Instead will be reti here. Instead of ret return instruction, right? It will be reti. Return from interrupt. This return from interrupt will exit this subroutine ISR, this small subroutine, and it will return to the main program. How it will return to the main program? Whatever value it has stored, whatever memory location it has stored in stack memory, it will pop that memory location. It will pop that. It will read that memory location, and it will store in program counter. So now the program counter memory location will be 2002. First it will store 20, then it will store 02. It will be 2002H. Then it will execute the instructions in the main program starting from memory location 2002H. Concept is same, except of instead of RET instruction, we are using RETI instruction, return from interrupt. That is the only difference. We have already gone through this concept in our previous class, how the call instruction executes and how the return instruction executes. Concept is same. Instead of RET instruction, we are using RETI instruction, return from interrupt. That is the only difference. Clear here? So this is how it will execute the RETI instruction. RETI instruction, right? Returns the control to the main program after servicing the interrupt. Description of this instruction is used to return from the ISR, that is interrupt service subroutine, that was called as a result of interrupt occurrence. Whenever there is any interrupt, so this ISR is called, a small subroutine, a small program is called. It will execute this subroutine or a small program, and the last instruction is RETI, return from interrupt, wherein it will exit the subroutine and it will return to the main program. The main program execution will be started, or it will resume from the point where it was interrupted. This is RETI instruction. This instruction is clear here. RETI instruction. Any doubts here in the RETI instruction? Is it understood? Yes, is it understood here?
Yes, sir.
Okay, fine. Let us move on to the next instruction, AJMP, absolute jump. So this is similar to a call instruction, absolute call, right? The syntax of this instruction is AJMP target address, absolute jump target address. This instruction will transfer the program execution from the main program to the target address unconditionally. It will jump from the main program to the target address to the subroutine unconditionally, right? It is an unconditional jump instruction. A call, L call, they are conditional jump instructions. This absolute jump is unconditional jump instruction. Okay, so it will jump to the target address unconditionally. To jump to the target address unconditionally without any condition. Okay, similar to the A call, it is similar to the A call what we discussed in our previous class, right? But here the difference between call and jump instruction is, in the call instruction, after it jumps to the subroutine, it will return back to the main program. But in the jump instruction, when it executes jump instruction, after it jumps to the target address, it executes the subroutine, but it will not return back to the main program. It will not return back to the main program. That is the only difference between call instruction and jump instruction. Okay. So absolute call target address. Okay, absolute call target address. The syntax of absolute jump is absolute jump target address, right? So these are the jump instructions. both of them jump to the subroutine, but in the absolute call instruction, it will return back to the main program, but absolute jump instruction, after jumping to the subroutine, executing all the instructions of the subroutine, when the last instruction is not executed or there is no last instruction such as RET here for the AJMP, and it will come out of the program. It will not go to the main program. Okay, this is a difference between main difference between absolute call and absolute jump, or between call instructions and jump instructions. The description of this AJMP is the range of this AJMP instruction is within 2 kilobytes of the program memory. It will jump anywhere between 2 kilobytes. Okay, that is 2048 bytes. 1024, 2 into 10 raised to 6. Correct? 10 raised to 6. That is 1000, 2 into 1024, 2048 bytes. Right? So that many number of memory locations it can jump from the current program counter address. From the present program counter address, it can jump anywhere within 2 kilobytes of the memory locations. So AJMP transfers the program execution to the target address. How it will jump to a target address? The target address is calculated by considering the target address is calculated by considering the opcode bits, that is 7th to 5th bit. Right? It is a 2-byte instruction. AJMP is a 2-byte instruction. In the first byte, the opcode bits 7 to 5. The opcode bits 7 to 5, 7 to 5, that is D7, D6, D5 of the opcode, and the second byte of the instruction. Both are combined together and the target address is calculated. Are you following here? The D7 bit, D6 bit, and the D5th bit. MSB bit D7, next bit D6, and the next bit is D5. So these 3 bits of the opcode and the second byte of the instruction. Second byte of the instruction, these 2 are combined together to form the target address. Right? And to this target address, the jump will take place. So how the jump address is calculated or the target address is calculated? By combining the D7 to D5 bits of the opcode along with the second byte of the instruction. So altogether there will be how many bits? Second byte means it is 8 bits, right? And this 7 to 5 means 7, 6, 5, 3 bits. So totally it will be 11 bits. Correct? So that is what it is indicated here. The program counter plus 2. That is the address of the next instruction. Address of the next instruction is stored in program counter, and the target address is the 11-bit target address. 11-bit target address. How these 11 bits are obtained? We are taking the MSP 3 bits, the last 3 bits of the opcode bits among the 8 bits of the opcode, and the second byte of the instruction. We are combining these 2 to form the target address. Clear here? So this is how the AJMP instruction will jump to the particular target address based on the opcode bits and the second byte of the instruction. Similarly, we have LJMP instruction, long jump. The syntax of LJMP instruction is LJMP target address. Difference between AJMP and LJMP is AJMP can jump within 2 kilobytes of memory location, whereas LJMP can jump within 64 kilobytes of the memory location. This is the difference between AJMP and LJMP. LJMP full form is long jump. AJMP is absolute jump. So this transfers program execution to the particular target address unconditionally. There is no condition here. Okay, condition is not mentioned. At what condition there should be a jump to the target address? That is not mentioned. Okay, so that is called as unconditional jump. It is called as unconditional jump. Okay, so condition is not mentioned or not specified in the program. Without specifying the condition, directly it will jump to the target address, to the that particular target address or specified address. Range of this is within 64 kilobytes. It is a 3-byte instruction. Is 3-byte instruction. The target address is calculated by taking the first byte, that is by taking the second and the third byte of the instruction. First byte is the opcode. Next 2 bytes are the target address. Okay, so it is a 3-byte instruction as that of the LCall instruction. LCall is also 3-byte instruction. LJMP is also 3-byte instruction. So the first byte is the opcode. The next 2 bytes, it is second byte and third byte. They are for the target address. It will take the second byte and the third byte of the target address as a target address and it will jump to that particular address. The difference between LJMP and LCall is that a call instruction returns and continues execution with the instruction following the call, whereas jump will not return. That is what I told. The call instruction returns and continues execution in the main program, whereas the jump instruction will not return to the main program after executing the last instruction of the subroutine. Clear here? So how the target address is obtained? So target address is the 2-byte target address. It's a 2-byte target address. So that is bit 15 to 0. Okay, 15 to 0, 16 bits or 2-byte. Second byte and the third byte. So total 16 bits, 15 to 0. That is the target address. It is loaded into the program counter. And once it is loaded into the program counter, the controller or the microcontroller will jump to that particular target address. Next is SJMP, short jump instruction. The syntax is short jump target address. Short jump target address. So this is similar to the other jump instructions, except here the jump will take place between -128 to +127 bytes. -120, that is 256 bytes. It is just 256 bytes, not 2 kilobyte or 64 kilobyte. Right? The jump will take place. The range of the SJMP instruction is between -128 to +127 bytes. In examination, they may ask what are the ranges of the different call and jump instructions. So they have to mention the ranges of these call and jump instructions, whatever we are studying here. For example, if the range of the AJMP is 2 kilobyte, here whatever we are studying, then LJMP range is 64 kilobytes, and this SJMP instruction ranges between -128 to +127 bytes of the program counter. It is a 2-byte instruction. Here the target address is calculated by considering the program counter, that is next instruction memory location of the next instruction, that is memory location where the next instruction is stored, that memory location plus the relative address. Right? I gave an example in the previous classes how the target address is calculated. Okay, by adding the relative address to the program counter address. Program counter will have the address of the next instruction, that plus the relative address, that will give the target address. I give the example of J and Z next. That example we took, right? And where we calculate the memory location of the next instruction is 2006. Second byte is 03. Second byte is 03. So that example, whatever we have taken, it is, we have written some instructions here. Let us say org 0000h, right? Then move a comma hash 23h. Some instructions we have written like this. Right? Then here I am using the say is the instruction that we are studying here, SJMP. So it is SJMP. Suppose I mention it as next. So where this next should go, or what is the target address? Let us say SJMP next instruction is stored in memory location 2004. Okay, so in 2004 memory location, first byte, that is the opcode, is stored. For SJMP next, let us say the opcode is 47H. Opcode it is. Okay, operational code. Then next instruction after SJMP, let us say I am using the instruction SUBB a comma hash 05H. Right? Then there is a target address where I have written a small program or a subroutine. Okay. So I have written a subroutine starting from org. Let us say this address is 2009. In this 2009 memory location, I have used many instructions. Some instructions say move a comma hash 59H. Some instructions I have written then ADDC, 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 A comma hash 088, something like this. Right now I have to calculate this address 2009. To obtain this, what is done is, so first byte is 47H SJMP next instruction, that is the opcode. The second byte, it is stored in 2005 next memory location. Let us say this is 03, 03. Okay, so the address of the memory location SUBB instruction next instruction is 2006, 2006. Now, if we want to calculate the target address or the jump address, then how to calculate that? What we have to do? What is the program counter now? Next memory location, that is 2006, address of the next instruction SUBB A,05, it is 2006. Program counter is now storing 2006. So to this, what is done is relative address is added. Relative address is the second byte of the instruction, jump instruction, SJMP instruction. So let us say it is 0. So this will give us 2009. 2009. So what is this 2009? 2009 is the memory location where the subroutine is stored. So this is our subroutine 2009H. In this subroutine, there is a small program consisting of few instructions, right? Where we have used certain instructions, and after executing all the instructions, it will not return to the main program, but it will directly end the program here. There is no return instruction for the jump, but there is return instruction for the call instructions. Okay, remember, there is no return instruction for the jump instructions, but there is a return instruction for the call instructions. So this is how the jump instruction will execute, and in particular, this is SJMP instruction. Concept is clear here, how SJMP is executed? Yes, concept is clear here. Understood the concept? Abhishek? Abhishek? Understood the concept? Basuraj Gadkari? Basuraj? Basuraj Ainapure? Basuraj Ainapure? Understood the concept here? Concept is clear? SJMP instruction. Bhagyashri? Bhakti? Bhakti?
Sir, once again explain.
Okay, I'll explain it once again. See here, I have typed a few instructions. So my first memory location is org0000H. This is the starting memory location. That means the first instruction move A, hash 23H is stored starting from the memory location 0000H. Right? So as I'm going on executing here, I'm using the jump instruction, that is SJMP next. Right? So this SJMP next instruction is stored in the memory location, say 2004H of the program memory or the ROM memory. In ROM memory or the program memory 2004H memory location, the SJMP next instruction is stored. So what is meant by the instruction is stored? We already know that the opcode or the operational code of the instruction is stored, not the instruction. Okay, we know that the microcontroller will not understand the English language which is understood to the programmer or to us, but it will understand only the language of binary or the opcode or the operational code. So the opcode for the SJMP next is say 47H. This is the first byte. This SJMP next is 2-byte instruction. It will take 2 memory locations. It will take 2 memory locations. In the first byte, it is storing the opcode. In 2004 memory location, it is storing the opcode. That is 47H, operational code of that particular jump instruction. SJMP next opcode is say 47H. Clear here? Then the next byte, what is the second byte then? Second byte is called as the relative address. Second byte is called as the relative address. SJMP next has 2 bytes. First byte is the opcode, second byte is the relative address. So this relative address is stored in the next memory location, that is in 2005. In 2005, it is storing the relative address say 03. Okay. Now, if we want to calculate what is the next address or what is the jump address or what is the target address, right? Where this SJMP should jump to which address subroutine it has to jump to. That we have to calculate. So to calculate that, what is done is the memory location of the next instruction after the SJMP instruction. The memory location of the next instruction of the instruction after the SJMP instruction. After the SJMP instruction, next instruction is SUBB A,#05H. Where this is stored, this instruction is stored, let us say in 2006, next memory location, immediate next, right? 2004, 2005 is for SJMP, next, immediate next is 2006. In 2006 memory location, SUBB A,#05H is stored. Now to find out the target address, this memory location is taken, that is 2006, plus the relative address, that is 03. We have to add these two to get the target address. So now our target address is 2009. It is 2009 is the target address. We have calculated the target address. So in this target address 2009, there is a small subroutine, a small program which consists of few instructions, right, to perform a particular job, to perform a particular task. Now the instructions I have stored in 2009 is first instruction move A,#59H. Then in next memory location ADDC A,#08H. There are few instructions. After executing all those instructions, the last instruction is end, because there is no return instruction for the jump. Jump will never return back to the main program. Its job is only to jump to a target address, execute that subroutine, and get the job done. Okay, that's all. And it doesn't return back to the main program. Clear here?
Yes,
So
sir.
this is how. Now understood, Bhakti?
Yes, sir.
Okay, fine. Others, I hope everybody understood here. Other students. Mantesh, is it understood?
Yes,
Mantesh?
sir, understood.
Okay. Priyanka, understood? Priyanka? Shodhan? Shodhan?
Yes, sir.
Is it clear yet? Okay.
Yes, sir.
Okay. Rohit Alwani? Rohit Alwani? Understood? Rohit? Vaishnavi? Vaishnavi? Is it clear yet? Vaishnavi? Okay. So let us move on to the next one. So this is about the SJMP. That is what it is. The description of that is mentioned. First byte is the opcode. Second byte is a signed number displacement. That is the relative address, which is added to the program counter of the instruction following the SJMP to get the target address. This PC plus 2 will be the address of the next instruction that will be stored in program counter. So this program counter address plus relative address, that will be the target address. That will be the target address. Fine. Let us take up a small program. We are asking about the Fibonacci number here, the program of the Fibonacci series. Right. So to store first 10 Fibonacci series, to store first 10 Fibonacci series here. Now, what is a Fibonacci series? Fibonacci series, let us start from 0 and 1, first two numbers. 0 plus 1 is 1. If you add previous two numbers, you'll get the next number. Okay. Then 1 plus 1 is, I have added these two. These two I have added to get the next number. Then I will add 1 plus 2. These two I will add, previous two. I will get the next digit, that is 3. Similarly, 2 plus 3, 5. 3 plus 5, 8. 3 plus 8, 13. Then 8 plus 13, 21. 21 plus 13, how much it is? 34. 34, okay. Let us consider these first 10 Fibonacci series numbers. Now, first number is 0 here. First number is 0. Second number is 1. Second number is 1. How to obtain the third number? Third number is nothing but first number first number plus first number plus the second number plus second number. Okay. Similarly, if we want the next number, that is the fourth number. Fourth number, if we want, then how to get the fourth number? Second number plus third number. This second number plus third number. Second number plus third number. Now I have to generalize this. This is the logic of the program. Right? Now, how to generalize this? If I want the nth number, if I want the nth Fibonacci number, so to get that, what I have to do? So nth number 4 is here. It is 4. Here it is 4 minus 2. So it is n minus 2. So this is n means it is 4 here. So 4 minus 2 is second number. That is n minus 2th number, n minus second number, n minus second number, okay, plus next one. How will get the 3 here? 4 minus 1 is 3. It is n minus 1, n minus 1th number, This is a generalized formula for the Fibonacci series generation. Now let us write the program. First is the initialization. Move R0. I will take the count as R0 to store the count. So first 10 digits. So instead of storing it as 1, I will store it as 8. I will tell you the reason for that. Next, move R1, hash the memory location. Let us say these values are stored starting from memory location 20H. These numbers, right? I have stored them in memory location 20H. Okay. So now in 20H I have stored these numbers. Move R1, hash first memory location, that is 20H, pointer to the first memory location. Okay. So R0 is 8, R0 is 8. Then next here R1 is 20H. Okay. Then move at R1, hash 0, hash 0 or hash 0. It is okay. So I am moving the first number in R1. At R1 means in the first memory location, that is in 20H, I am storing the first value, that is 0. Okay. Then I will increment to get the next value, that is 1. I have to get the next value. Increment R1. Yes,
Sir.
please.
ಸರ್ ಅದು ಡಾಟಾ ಪಾಯಿಂಟರ್ ಯೂಸ್ ಮಾಡ್ಕೊಂಡು ಮಾಡ್ಬೋದಲ್ಲ ಸರ್, ಒಂದು ಸಣ್ಣ ಪ್ರೋಗ್ರಾಮ್ ಬರೆದು
ಏನಂದ್ರಿ ನಂದೀಶ್?
ಡಾಟಾ ಪಾಯಿಂಟರ್ ಹಾಕಿ ಮಾಡ್ಬೋದಲ್ಲ ಸರ್ ಅದನ್ನ?
ಮಾಡಬಹುದ್ರಿ. Anyway, you can do it in any method. This is one of the method. This is of one of the method. You can, if your logic is correct, until and unless your logic is correct, you can do by any instructions, by any method. There is not a problem. Your logic should be correct. Okay, if it is satisfying this logic, whatever this logic is there, if it is satisfying this logic, that is first number is 0, second number is 1, third number you are obtaining by adding the previous two numbers, fourth number is second number plus third number. We are generalizing this to get the nth number is n minus second number plus n minus 1th number. So if this logic is correct, until and unless you use any instructions or any method, it doesn't matter. Okay, you can use any instructions, any method you can use. It is irrespective of any method, any instructions. If your logic is correct, provided if your logic is correct, right, then it is fine, no problem. Clear here, Nandish?
Yes sir.
Okay.
Yes sir.
Okay. Increment R1. So increment R1. So R1 will be equal to what is there in R1? 20H plus 1. 20H plus 1. This will give us 21H. 21H. Okay, 21. That is the second value. Now I will move the second value, that is move at R1 in 21H memory location. I am moving the second value, that is hash 01 or hash 1. Okay, so So R1 at R1 means which memory location? In 21H memory location. In 21H memory location, 21H memory location, I am storing the value 1. That is the second number of Fibonacci series. Fine. Then next, I've stored these two numbers. Then next, I have to get the next numbers. So to get the next numbers, what I'm doing here is move A comma at R1, move A comma at R1. So at R1, what is there in R1? 1 is there. The second number 1 is there. Okay, so I'm moving this in A register. A is equal to 1. At R1 means at memory location 21H. So the value I'm moving in A register 1. Then I have to decrement now because I have to add 1 with 0. Okay, 1 with 0, if I add this number plus 0, then I will get the next number, that is 1 I will get. Yes or no? So I will add this to 1. To get the previous number, I have to decrement. Decrement R1, decrement R1, decrement R1. R1 will be equal to 21H minus 1. That is 20H. 20H. We got the previous memory location. Now I will add. Now I will add the two values. That is second number plus the first number. Add A comma at R1. A comma at R1. This is nothing but A is equal to what is there in A. Just see what is there in A. Just now we have written 1. That is the second number. So A is equal to second number, that is 1 plus at R1. That is at 20H. 20H we are having 0. First number. 0, this is equal to 1. This will be stored in A register. Now from this I have to move it to the next memory location. Correct? So this 0 plus 1 I got. Where is 1 stored? 0 plus 1, 1. Where it is stored? In memory location 22H. 20, 21, 22. In 22H, 1 is stored. That is the addition of 0 plus 1. Yes or no? Then I have to get that memory location. So to get that 22nd memory location, now we are in 20H memory location, 20H. To get that memory location, I have to increment R1. 2 times I have to increment R1. Increment R1. 2 times to get the 22nd memory location, 22H memory location. Increment R1, this will give us R1 is equal to 20H plus 1. 20H plus 1, that is 21H. Then this increment R1, next one, this will give us R1 is equal to 21H plus 1, that is 22H. Now what I will do is, I will move the whatever result I have got, 1 plus 0 or 0 plus 1, that I will move into this particular memory location. This 22H memory location. Move at R1, comma A. This at R1 means in memory location 22H, value of A will be stored. Value of A is 1. Now I have to check the count. DJNZ, R0, count is there in R0. Count. I have stored it in R0. 8. I have taken 8. R0, comma back. Now this R0 I have taken it as 8. The reason is, see here. So 0 plus 1 is 1. 0 plus 1 is 1. Now we are at this particular value. Okay, we already got 3 values. Still how many values are remaining? We are generating 10 numbers, Fibonacci numbers. Still how many values are remaining?
7.
7 are remaining, correct? So to get the 7 numbers, what should be my count, first value? If I take 10, will I get 7? If I decrement the count to 10, 10 minus 1 will be 9. But here how many values are remaining still? 1, 2, 3, 4, 5, 6, 7. 7 values are remaining. Correct? So if I take it as 10, 10 minus 1 will be 9. I will get 9. So that will not satisfy my count here. That is why what is done is, instead of taking it as 10 as the starting count value, I will take it as 8. Okay, so if I decrement this, then I will get 7. Still 7 values are remaining. 2, 3, 5, 8, 13, 21 and 34. Clear here? So that is why I have taken the count as 8 but not 10. Mantesh, is it also understood here? Mantesh?
Yes, sir.
Mantesh.
Yes, sir. Yes, sir.
Huh? Okay. So now where this back should come? Back, just see where it should come. First two numbers we are storing them, right? First number is 0 0, then second number is 1. Now where this back should come, to which instruction? Where we are considering the number with the previous number, we are adding them, right? So this back should come here. Considering the second number that we are adding with the previous number, right? It should come to this number. Second number is coming here at a comma at r1. Then we are decrementing the memory location to get the previous value. We are adding the present value with the previous value. Then what we are doing, the result whatever we are getting, we are incrementing the memory location 2 times to get the next subsequent memory location. In that memory location we are storing the result. We are incrementing 2 times, increment r1, increment r1. We are storing the result, we are decrementing the count. So now first time, what is the count? When the previous 0 plus 1 1 we are getting, the count is 8 minus 1, that is 7. Second time when you are executing the loop, second time when the loop is executed, it will be 7 minus 1, that is 6. Now just check whether it is telling. Second time what you are getting, 0 plus 1 1, 1 plus 1. So this one will be added with previous one to get it 2, to get it 2. So we are getting these 4. Still how many are remaining? Just check. 1 2 3 4 5 6 are remaining. So this count will be 7 minus 1, that is 6. 7 minus 1 is 6. Clear here? So this is how it will execute the subroutine, right? It will execute for 8 times, and after it executes 8 times, you will get the count here, that is 0 1 1 2 3 5 8 13 21 and 34, the 10 first Fibonacci series numbers. Is it understood here, this program? Yes, please. This program is understood here?
Yes, sir.
Okay, fine. Abhishek Palekar, is it understood? Abhishek Palekar? Aishwarya? Aishwarya? Is it understood here? Shabaz? Shabaz?
Yes, sir. I understood, sir.
Understood? Fine. Shafia?
Yes, sir. Understood.
Okay. Take one program for homework here. Just try it out home. We'll discuss in the next class. This program, write an ALP to find the sum of 20 bytes, write an ALP to find the sum of 20 bytes stored in an array of external RAM starting with address 2000H. Store the 16-bit sum at the end of the array. Write an ALP, assembly language program, to find the sum of 20 bytes stored in an array of external RAM starting with address 2000H. Store the 16-bit sum at the end of the array. Think about this first. Understand the logic of this. That once you understand the logic of this, write down the instructions, right? And accordingly, you have to structure the program. That is, program should be written by understanding the logic and then writing the instructions. Okay. Taken this in statement here, write an ALP to find the sum of 20 bytes stored in an array of external RAM starting with address 2000H. Store the 16-bit sum at the end of the array. All of you taken this?
Yes, sir.
Okay, fine. In today's class, we discussed about the jump instruction, that is AJMP, LJMP, and SJMP, and one more return instruction, RETI, return from interrupt. Then we have discussed a program on the Fibonacci series, right? In the next class, we will take up few more instructions, that is jump instructions, and then if possible, we will take up the programming part. Okay. Meanwhile, you complete this program, write this program. We'll discuss about this program in the next class, right? Any doubts here? Anything not understood? Any doubts here? Yes, please. Any doubts?
No, sir.
Okay, fine. We'll wind up the session here. We'll continue in the next class. Thank you.